Bismillahirrahmanirrahim. In this course module, we will start learning the concepts of linear algebra. We begin by introducing vectors. How do we represent vectors? What are the applications in which we can represent data using these vectors? And what are the basic vector operations? Since this is the first module of the course, I will start with one machine learning example. Consider a problem in which we're given a photo of a person and we want to find out whether he or she is smiling or not. So this falls in a category of emotion detection, that you want to find out whether the person is happy or sad, smiling or not. Or another problem could be, given a photo, you want to find out whether the person is sleeping or not. It simply means you want to find out whether the eyes are open or eyes are closed. So before we formulate this as a machine learning problem, let me give you a quick demo as a solution of this problem. Let me give you a demo of this problem in which we want to detect whether the person is smiling or not, or whether the eyes are open or closed in real time. So let me enable these features. So I'm using Luxent Face SDK, which is commercially used in a variety of applications. So here we can say that eyes open percentage, and here we have smile percentage. So I'm not smiling for some reasons, but if I open my eyes wide, it is close to 100%, and if I slowly close my eyes and open again, so that's how it works. So this is just a demonstration of the problem. We revisit this problem and we want to formulate this problem as a machine learning problem. In terms of machine learning, this is a classification problem because we have two classes here. Given a photo of a person, we want to find out whether the person belongs to a class of smiling people or a class of people who are not smiling. So we have two classes here. In fact, for each of the problem, we have two classes. So in any machine learning problem, we have different steps. Let's talk about those steps. So in the first step, in every machine learning problem is data gathering. So we want to gather data. So for example, if you have a problem in which we want to find out the person is smiling or not, so we want to get photos of different persons and we want to label the data, label those photos, whether in some photo the person is smiling, in some photo where the person is not smiling, or in fact we can even quantify what is the percentage of the smile in each photo. So once we gather data, the next step is we want to extract useful features for each of the photo. What do we mean by useful features? So just to demonstrate this concept, say we have this photo, and on this photo we have marked these points here. In fact, so these points represent features of this photo, or for any photo we can have these markers, or we can have these points on each of the photo. So the relationship between these points in fact enables us to determine the person is smiling or not, the eyes are open or not, and so on and so forth. So once we have the data, we have extracted useful features of the data, and once we have these features, the next question is how can we use these features. The next step in any machine learning problem is that we want to develop a model that takes input these features or these photos, and the model learns from the data that if the model gets new photo, that photo would belong to which class of the problem. So step 3 would be, so we choose a model that can best capture, that can best fit the given problem or the given data. And finally, the step 4 would be we want to train and evaluate model. So we have a model, so using data we train a model, and then we can evaluate the accuracy of the model. To illustrate further, maybe we choose one problem uh, that, given a photo, whether the person is sleeping or not, or we want to determine whether eyes are open or closed. So to illustrate this, say we talk about eyes open closed problem, and so I have zoomed in to the eye feature of the photo, right? So if you see this, so if the person eye is open, the distance between these 2 points would be larger, and the distance would approach 0 if the person eyes is closed. So once we have these images, in fact, we just want to find out that what is the difference between these 2 points in each photo, uh, whether the person is sleeping or whether the person is not sleeping, or the eyes are closed or eyes are open, right? So the step 2 is we extract useful features and then we develop a model. So in this simple case, a model would be very simple, right? Say we have a large amount of data that is labeled, and we represent that data, say, in a two-dimensional plane. So we say for each photo we determine whether the eyes are open, the eyes are closed, right? And that simply means we want to find out what is the distance between these 2 points. Say we take two axes. Say on x-axis we have left eye, on right axis say we take right eye, right? And we determine the distance between these 2 points, and we plot the distance between these 2 points for left eye on x-axis, and for right eye we plot on y-axis. And for each photo in the label data, we use circle to denote a label for which eyes are open, and triangle for closed eyes label, right? And if we plot data, we will be getting something like this. See, so eyes would be open, the distance would be larger for both left and right eye, and if the eyes are closed or close to the distance between these 2 points is close to 0, so this triangle would be somewhere here, right? So once we have this graphical representation of the data, or once we have some information about the data, the next step is develop a model, right? And so once we have a model, so we train and then we evaluate a model. But the question here is, what should be the model here? So we can see the points here can be easily differentiated using a straight line. We say in this simple case, we choose a model and that separates these blue circles and red triangles. So this green line would best differentiate or would separate these two classes. So once the model is trained using the data, and you know that this is the best boundary that well separates these blue points and red triangles, so we can take a new photo, and we can predict whether in the new photo the person is smiling or not, right? For example, you get a new photo, and for new photo, say you get 3 new photos and you get these 3 points for those 3 new photos. So for this photo, you can say that in this photo the eyes are open, in this image the eyes are say 50% open, 50% closed. Here the eyes are almost 90% closed or 10% open, well, something like that, right? So this is just to give you an illustration that how do we solve problem in machine learning. But there are very fundamental questions here. What is the best model, or how do you train the model using the label data, and what is the accuracy of the model? How do we measure the accuracy of the model? Can we get a better model? How do we split train and test data. So we will answer all of these questions as we progress in the course. But to learn all of these concepts, we will start learning the fundamental concepts. Let's start learning about vectors. So we define a vector as an ordered finite list of numbers, and those numbers can be real or complex. In this course, we will only talk about real numbers. So we represent vector using a letter symbol, and we stack the list of numbers in an ordered form. For example, a vector of 4 real numbers can be represented in this form. So using these, we have stacked these numbers using these square brackets, or in some textbooks, we also use these round brackets and we stack these numbers. And in fact, these numbers can also be stacked in a horizontal fashion. So these different notations appear in different textbooks or in different research articles. But we will stick to the first notation in this course. So we also define what do we mean by size of a vector. Number of elements the vector contains is the size of a vector. So we also refer to this as length or dimension of the vector. We usually express a vector of size n as a vector that belongs to Rn. For example, a vector b of size n, so we can also write it as b belongs to Rn. So Rn is, so R here represents real number, and n here, n in the superscript denotes that there are n number of real numbers stacked in a vector b in an ordered fashion, and we call it n vector. So there are different names. So b belongs to Rn or n vector. So we will be using these terms interchangeably. So we also define the notation to represent entry of a vector. So we use bk, b subscript k, to denote the kth entry of the vector b. For vector a, for example, for this vector a, so the second entry a2 is 30.1 for this vector. So let's also define some special vectors. So we begin by defining zero vector. So a vector in which all entries are zero, as the name suggests, we call it zero vector, and we denote using this by 0 belongs to Rn. So it can be in R1, it can be in R2, it can be in Rn. So we also define one vector. As the name suggests, if all elements are equal to 1, we denote it by bold 1 that belongs to Rn. We also define unit vector. In fact, we're going to define standard unit vector. That is a vector with all elements 0 except one element, and that element is equal to 1. And we use special notation to represent a standard unit vector. So we use this ei belongs to Rn, and this ei is defined as we said earlier. So all elements are 0, so only one element is 1. And for ei, the ith element is 1 and all other elements are 0. So mathematically it is defined as using this piecewise function. So this is 1 when I is equal to j and 0 when I is not equal to j. So jth entry of ei vector is equal to 1 when I is equal to j and 0 when I is not equal to j. And we can compactly write this as delta I comma j. So this delta is referred to as Kronecker delta. So delta ij is equal to 1 when I is equal to j, and delta ij is equal to 0 when I is not equal to j. So it's simple. So k sparse vector, a vector with at most k non-zero entries. We can also interpret the vector as a point in a geometric space. Say we have a 2 vector and this, since it's a 2 vector, that belongs to R2. So any 2 vector can be represented as a point in this 2-dimensional space. So we can represent this 2-dimensional space using these 2 standard vectors. So we call it we call this label as x-axis, and this vertical axis is y-axis. But in this course we'll label the horizontal axis x1 and vertical axis as x2. So in this R2 plane, we can label different vectors. Say, okay, E1, that means a standard unit vector for x1 axis. This vector, this point, can be represented along this x1 line. So this point here, where the value of the first coordinate is 1 and second coordinate is 0. So this is E1. Right. Similarly, we can label E2. Say E2 would be somewhere here. What about 0 vector? So if we talk about 0 vector, 0 vector is at the origin, or where x1 is equal to 0 and x2 is equal to 0, right? And what about 1 vector? So one, we know that one is x1 is 1 and x2 is 1, so it's somewhere here. So this is 1, right? And in fact, any point, any 2 vector, say we can choose some vector. We can say, we can take a is equal to, say we take 1 and 2, and this is in fact shown by, so this point here. So you can denote with a point, or we can also draw a line that is pointing from the origin in this way. So this point, or this vector, is a vector A. This was the geometric interpretation of a point in a 2-dimensional plane. A 2 vector can be represented by a point in a 2-dimensional plane. Similarly, we can talk about 3 vector. Any 3 vector that consists of 3 entries, 3 real numbers, can be represented by a point in a 3-dimensional space. So, okay, to be consistent, we say this x is x1, this x is x2, and this is x3. This is a 3-dimensional plane, and we take, for an example, we take a vector A is equal to -2, 1, and 2. This point would be represented by this vector would be represented by a point in this plane. That is, so along x1 we have -2, so, and we have along x2 we have 1, and along x3 we have 2, somewhere here. This vector would, this point or this vector is vector A. Okay, so what is the interpretation of different entries of a vector? For example, we had 2 vector A, the first entry was 1 and the second entry was 2. So if you see the first entry, that quantifies the contribution of a standard unit vector E1 towards vector A, and second entry of the vector A quantifies the contribution of E2 second standard unit vector towards A2. We can extend this concept and say we take a vector A that belongs to Rn, and this vector would have n components and entries, so A1, A2 up to An. So A1 quantifies the contribution of a standard vector E1, and A2 quantifies contribution of E2, and so on and so forth. We can write An, En. So this is just a geometric interpretation of vectors. Let's look at some application examples in which the data is defined using these vectors. So for example, the location anywhere on Earth can be represented using a coordinate system which we call latitude longitude system. That is in fact a vector with respect to this coordinate system. So this point here, this is called the center, or this is 0 latitude, 0 longitude. And if you move along this y-axis, you move towards north in degrees. If you move along this axis, you move towards south in degrees. So for example, we are sitting somewhere here in Lahore, and which is in fact 31.5 degree north and I think 74.3 degree east, and that can be represented by this vector. In fact, it's a point. Point is a vector. We already know this, right? So a location anywhere on Earth is in fact a vector. Other examples include displacement, velocity, and acceleration. For example, you're traveling along this blue line, and you have different orientations, and you reach this point. So this is the distance you have covered, but in terms of displacement, so you have covered the shortest distance, which is given by this green vector. So this green vector is a displacement, and displacement, velocity, acceleration, each of these quantities are represented by vectors. Other examples could be, say we have a color. Each color is represented by 3 vector. We're talking about RGB here. So we know that each color has 3 components: red, green, and blue, and therefore we can represent each color by 3 vector, where each value represents the contribution of each of the primary color. Other examples could be quantities. An n vector, a vector of size n, say call it q, can represent the amounts or quantities of n different resources or products that can be held, that are held, produced, or required by an entity such as a company. For example, n vector represents the quantity of n products stocked in different warehouses of a company. So that could be that is an example in which n vector represents quantity. Another example would be a vector can represent values of some variable across population. It simply means you have a vector of size n, and that can give the values of some quantity across some spatially distributed population of individuals or entities. For example, n vector a can represent the blood pressure of a collection of n patients, with each entry ai denotes the blood pressure of the ith patient, and we have n number of such patients. So the values across population can be stacked in a vector as well. Another example would be, in fact, images can also be represented as vectors. So we know that image has columns and rows, but we can stack those values in the form of a vector, and we can represent image as a vector as well. Another example would be time series. So let me comment on this word time series. So a time series represents any quantity data signal that has variation over time, that varies over time. Example could be a 12 vector can represent the average monthly temperature or rainfall or pressure, say, of any city. So we live in Lahore, so we will say a vector of size 12 can represent the average monthly temperature, rainfall, pressure of Lahore. And for example, so this is the plot I have for temperature and rainfall data. So this red line denotes, so we have 12 points. So we have average monthly temperature of different months from January to December. So this is the peak of a summer, and these blue bar graphs indicate the rainfall data for Lahore. So this region here we have the monsoon season. Yeah. So in fact, uh, any quantity that varies over time can be stacked, can be represented in the form of a vector. Another example would be, say, a vector of size 30 can represent the number of expected COVID-19 patients in Pakistan over the next 30 days. And ideally, we would like to see that this number should decline from index 1 to 30. This is our wish list. Other examples could be exchange rate, audio, and in fact, as I said earlier, any quantity that varies over time. Other examples of vector could be found in audio. An audio signal, as we get an audio signal that varies over time, so audio signal is in fact a vector. So this is a plot of a signal of a sound flute, and this is plotted versus time, and the signal is sampled at a rate of 44,100 samples per second. So we have an 8-second signal, so a size of vector would be 8 times 44,100. And there is a reason why do we use 44,100, and in fact in digital audio we use 48 kilohertz and 92 kilohertz. In fact, we also use 190, I think 192 kilohertz as well. And maybe you can have a read that why do we need these high sampling rates to sample an audio. Okay, another example in which we use vectors to represent data is feature or attribute. So we have seen an example today in which we have a classification problem. In classification problem, we collect features from the data, and we stack those features in the form of vector. So in emotion recognition, the person is smiling here, the person not smiling here, and we get these features for each image, and we stack these features in a vector, and we refer to this vector as a feature vector. These were just some examples, and I hope now you can connect the concept of vectors to data in these applications. Let's look at some of the basic operations on vectors. Among the operations on vectors, addition is the most fundamental operation. So we define addition of two vectors, say A belongs to Rn and B belongs to Rn. So two vectors of same size, so we can add these two vectors as we add scalars. So we define a new vector C, which is the sum of A and B, and entries of Ci is related to A and Bi as simple addition, and we have for this, for I is equal to 1, 2 to n. It simply means we have element wise addition when we add two vectors, or component wise addition. You can say C is given by A1 plus B1, A2 plus B2, and so on, AN plus Bn. And what we know about addition is that addition is commutative, and addition is associative. And you know what do you mean by these two terms? So commutative means A plus B is same as B plus A, and simply follows from the definition, or A plus B plus, say, D is equal to A plus B plus D, and it again simply follows from the definition of the addition of vectors. So geometric interpretation of the vector is that, say we are in R2 and we take two vectors, maybe for convenience we take E1 and E2, right? So this would be e1, and this would be e2. So we can use this new vector, and this is, say, e1. So we can sum of e1 and e2, and we know that the sum is given by this point here, and that is simply given by this vector. And if we see, in fact, we can also draw e2 here. So this is e1 plus e2, and you have been studying this in high school, that head to tail rule when you add two vectors in R2. Let's talk about one more operations on vector called scaling. Scaling of a vector by a scalar. Say we take a vector a that belongs to Rn, and we take a scalar, say beta, that belongs to R. So beta is a scalar, a is a vector, and we define scaling of a vector a by a scalar beta as beta times a, and this returns a vector, and that vector has the same size as vector a, and let's call this vector as, say, vector b. So b is defined as the ith entry of b is given by beta times ith entry of a. We can say scaling of a vector by a scalar simply means each entry, each element of the vector is scaled by the same value, right? So beta times a given by beta times a1, beta times a2, and beta times an. This is simply a scaling of a vector by a scalar, and the interpretation is maybe we can talk about interpretation R2. Say we take a vector, this vector, and we call this vector a, right? And what's happening with the scaling operator? So if you choose beta greater than 1, and when you multiply a by beta, this is going to extend the vector a, this is going to expand the vector a in the same direction. And if you choose beta between 0 and 1, this is going to shrink the vector a, right? So for example, 0.5a would be this one, and say 2 times a would be this. And if you choose beta negative, we again have a scaling operation, but the direction also gets reversed. For example, minus a would be given by, this is minus 1 times a, so direction also gets reversed. So this is just a geometric interpretation of a scaling operation in R2, and we can formalize this as, so when magnitude of beta is, say, less than 1, so we can say we have shrinking, and when magnitude of beta is greater than 1, so we have expansion, and when beta is negative, so we also get a change in direction. And furthermore, we also note that the scaling is commutative. That simply means beta times a would be same as a times beta. So, and also scaling is distributive over addition. Using additivity and scaling, we can define one or more operations on vector, which we call linear combination of vectors. So we can say that if we have vectors a1, a2, say am belongs to Rn, and we have scalars beta 1, beta 2, m number of scalars, and they all belongs to R. So a linear combination is defined as a linear combination of these vectors is defined as, so we say linear combination is given by beta 1 times a1 plus beta 2 times a2 and so on beta m times am. And we know that since a1 a2 am belongs to Rn, so this linear combination of vector would be a vector and that belongs to the same space. All right, and this is called linear combination. So one of two special linear combinations that we'll use very frequently, one is affine combination. So in affine combination, we restrict these weights that the sum of these weights beta 1 beta 2 plus beta m is equal to 1, because beta can take any values, but the sum of these weights, sum of these scalars should be equal to 1. And another combination is we call convex combination, in which we again would require sum to be equal to 1. Furthermore, we require each of these weight should be between 0 and 1 and should hold for each I. Let's also talk about geometric interpretation of this linear combination, affine combination, and convex combination. So for convenience, we again take R2 and we take this two-dimensional plane, and for convenience we take two vectors. Say this vector, we call it A, and we take another vector B, and we can draw somewhere, we can draw anywhere, right? In fact, say this is B, right? So what does their linear combination quantify, or what do we mean by linear combination of A and B? So we can say that we can linear combine any point in this R2 in this two-dimensional plane can be represented as a linear combination of A and B. So for example, so this point here, right? So this point can be represented as a linear combination of A and B. What do we mean by affine combination? So let me use magenta color for affine combination. So in affine combination, we require the sum of the weights should be equal to 1. That means affine combination of A and B would be given by beta times A plus 1 minus beta times B, and that is in fact can be also written as so we can say beta times A plus B minus beta times B, or B plus beta times A minus B. So we can choose any beta, and so this would be a vector, and this point can be anywhere on the line passing through A and B. And we can also talk about convex combination. So a convex combination, we restrict beta to be between 0 and 1. When you restrict beta to be between 0 and 1, that means a convex combination would consist of only points that are between B and A. So all of these points are between B and A. So this is a convex combination of vectors a and b. And in fact, every point of this line represents a vector in R2. Let's talk about another operation on vectors, that is inner product, which is most widely used operation on vectors. So let's define inner product for two vectors a and b in Rn. We define inner product using this notation a and b, which is also written as a transpose b. Although we have not defined this transpose operation, but we can for now you can just say that this is some notation a transpose b, and that is given by you multiply each element, you multiply element wise, and then you also add a1 b1 plus a2 b2 plus so on plus an bn. So this is how you define inner product. And by definition, inner product is commutative. That simply means a inner product b is same as b inner product of a, right? So inner product is commutative. So what is the interpretation of inner product? So inner product gives us a projection of one vector, projection of a on b or projection of b on a, and we will see this in more detail in a while, right? But first glimpses, say you have a vector a, we take vector a as a1 a2 and an, and take vector b as a standard unit vector ei, right? And we know that, and for convenience we take e2, and we know e2 would be given by 0, second entry is 1, and all other entries are 0, and b belongs to Rn. And when you take a transpose b, for this example, a transpose b or inner product of a and b would be given by a1 times 0 plus a2 times 1 plus a3 times 0. You only what do you get is a2. And if we recall, so a2 quantifies the contribution of e2 in a. So we can say when you take inner product of a and a standard unit vector e2, we get a projection of a on e2. This is just the first glimpse. We will talk about this in more detail as we progress. There are multiple operations which you can carry out using this inner product in different applications. Let's look at a couple of them. So maybe we are interested in say sum of elements. So sum of elements of a vector. That means you want, what do you want? a1 plus a2 plus a3 and so on and so forth. So see, you have vector a belongs to Rn. So you can take a sum of the elements by simply taking inner product of a and 1. And what you get is a1 plus a2. Okay, so this was very simple, right? Say if you want to take average of elements of a, right? So average of a, and which we will denote with a bar, or in some textbook, right, average of a. So average of a means average of all the elements of a. So we can define average of a using inner product. So average A would be simply given by a vector of ones times A, and you simply use a scalar here. Hang on, let me rewrite this. So 1 here is a vector, 1 over n is a scalar, and A is a vector. That was simply given by A1 plus A2 divided by n. That's how what you get is average of A. Similarly, if you want sum of squares, that is simply given by inner product of A with itself, and what you get is A1 square plus A2 square plus AN square. And this can be generalized as if you want a weighted average or a weighted sum. So we can say a weighted sum. Say you want to assign a weight W1 to A1 and plus W2 times A2 plus W3 times A3 and so on. And that is simply inner product of W and A. This is another interpretation of the inner product. Let me explain this further. Say we have an application in which we have two features. Say we have A that belongs to R2. So we looked at one example earlier in which we have facial features. So A contains facial features. Say we have 51 features, and we're only interested in the difference of say 30th feature and 31st feature that represents the feature of the left eye, right? So you multiply this vector, you take an inner product of A with a vector W, and we say W is given by 0 0 0 all entries. So on 30th entry is 1 and 31st entry is -1, the rest are 0, and W also belongs to R51. And when you take inner product of W and A, so what you get is A30 minus A31. Right, so this is just an illustration of the use of inner product. Another application would be in which we require, say, a price quantity sum. Say we have vector V that belongs to Rn, and vector P contains prices of n number of items, and you have vector Q in which that also belongs to Rn, and that quantifies the quantity you have for each of the product. And when you take inner product of P and Q, so what you get is a price quantity sum, or the total price of the quantities you have, right? So that would be P1 Q1 plus P2 Q2 plus Pn Qn. This was just an illustration of inner product. So we stop here, and we will continue with more operations on vectors in the next module. Thank you very much.